Go to chapter 11. Go to page. The reason I'm having you go on the book is just because it shows the chart which we need to look at. What the heck is it?
Super cooling. Phase diagram.
No, I don't care about those.
That's it. That's it. Critical temperature. What are we doing again? Wait, what? Lattice energy.
It must be chapter 10 then.
Condensation. Equilibrium vapor. Amorphous solids. Nope. I don't think so.
Go to page 377.
Wow.
377. Actually, 374. Go to 374. All right. Yeah. So, all ionic and metallic substances form crystal structures. Crystal lattice, which is repeating patterns. We've talked about that. So, this whole lattice energy term here is really important to understand. I haven't fully explained it yet. If you look at page 374, it's the very last sentence, essentially, of that 9.3. It says, a quantitative measure. What does quantitative measure mean? Yeah, but quantity means there's numbers involved. Qualitative is like you see a color change. That's qualitative. So quantitative measure of the stability of an ionic solid is its lattice energy. So in our notes, let's write lattice energy, defined as energy required to completely separate 1 mole of solid ionic compound into gaseous ions. That's what lattice energy is. Let's write that down. So lattice energy is the energy needed. And again, I obviously could just tell you this, and I have the notes, but I want you to see kind of how they explain it in the book, and there's a chart I want to look at. Energy needed to separate 1 mole of an ionic solid into gaseous ions. So the higher the lattice energy, the stronger the Coulombic force. So higher lattice energy equals stronger Coulombic force. And again, that's the positive negative attraction. Right underneath that paragraph, you see the Coulomb's law equation. Higher lattice energy equals stronger Coulombic force, which equals higher melting and boiling points. MP/BP, right? Higher lattice energy, stronger Coulombic force, higher melting point, higher boiling point. So if you look at page 375, it kind of works its way through explaining lattice energy. And there is actually thermodynamic principles here, which we will learn. So we're going to learn about lattice energy right now, but then when we get to thermodynamics, we'll kind of talk more about it. So I'm not going to go through every detail on page 375, but basically what it's showing, if you look at that number 1 there on 375, it says convert solid lithium to lithium vapor. So that requires 155.2 kilojoules per mole. So if you have 1 mole of lithium solid, that's how much energy it takes to vaporize it. Okay. And then number 2, it's saying, okay, if you have half a mole of F2, that's the energy required to turn it into F gas atoms, which is 75.3 kilojoules. And then if you keep going down further, to ionize it, so not only for lattice energy, not only are you separating the crystal apart, but you're turning it into ions, right? So now that's ionization energy. You're stripping an electron from Li gas, that's 520 kilojoules. You're stripping an electron from F, that's F minus now, so that's 328 kilojoules, but it's negative. I'm sorry, I said that backwards. You're giving the F that electron. So when you give it, it becomes more stable. So that's negative 328, right? So that's an exothermic process. So then if you combine those, you can get your delta H5, that's step 5, which is, okay, if I have Li plus and F minus and I put them together to make LiF solid, then what is the value of delta H? And then if you take the reverse of that, that is what lattice energy is. Again, I do not expect you to follow me right there, what I just said, all of that. I'm just sort of explaining and kind of breaking it down for you. There's all these energies involved with this one number, and again, it's going from solid to gas and then to ions. And that's essentially what lattice energy is. You're taking that lithium fluoride solid, turning it into a gas, then you're taking an electron from Li, but giving one to F minus, and what does all that energy add up to? That's the lattice energy. So if you flip the page, we will learn this. It's called Hess's Law. We will learn this, and I know it's probably confusing right now, and you're probably not with me, and that's fine. I'm just trying to start your brain starting to understand it, and we'll come back to this later when we do thermodynamics. But again, if you look at 1 through 5, all they're doing is just adding. You're adding all of those energies up, and that's the lattice energy for lithium fluoride. So if you want to separate LiF into the lithium ion and fluoride ion, that's how we figure it out, and that would be 1,017 kilojoules per mole. So if you have 1 mole of lithium fluoride, it would take 1,017 kilojoules per mole. And again, logically, where does that come from? Because it takes X amount of energy to turn lithium into a gas, X amount of energy to separate the F2 into Fs, X amount of energy to strip an electron from Li, X amount of energy when you give F an electron. And then, how much energy does it take to combine those two, right? The very bottom one there, the overall, and then to dissociate it. So again, you're probably confused, but that's fine. That's the logic of where these numbers come from. So if you look on page 377, that process for lithium fluoride would be calculated for all of those ionic compounds. LiF, LiCl, LiBr, NaCl, NABr. We're not going to do all the math. We're just going to go right to the final answer. What is the lattice energy? I just feel the need to kind of explain it a little bit. Look at the melting points. It's significantly higher. Look at magnesium oxide. Almost 3,000 degrees Celsius. That's crazy high. All right? Compared to salt, which is 801. And that's because the lattice energy is way, way, way higher, right? Salt is 788 and MgO is 3,890. What does that mean? It means it takes way more energy to separate magnesium oxide ions than salt. That's what that means. So if you understand that before we get out of here, that's good enough for today. All right? So the higher this is, the stronger that positive-negative attraction, the harder it is to melt it for boil. Okay? So, go back to page 374. So this applies to metals too. Metals have lattice energy. Ionics have lattice energy because they both use Coulombic forces. So, Coulombic force is calculated by this equation here. I know what they use, E. So it's Q, so there's a constant times Q times Q1, Q2 over R squared. So here's what this really means. If you have an ionic solid, this is your positive ion, this is your negative. So we'll just make up, we'll just say X and Y. So we have X positive attracted to a Y negative. So let's say our ionic compound is XY. Okay, so lithium fluoride, magnesium oxide, whatever. What two things, in this think math now, what two variables can we change to make F bigger, stronger? What can we do? Forget the K. The Q and the R. What can we do? How do we make F larger? You can make up any numbers you want. If I put 1 in for all of these, That'd be 1. How can we bring it
Make
above
Q
1?
bigger.
Make Q bigger. So we can make Q like 100 and 100, which is wild, but yeah, you can make Q bigger, and then what can you do to R?
Make it smaller.
So now explain, what does that mean? In terms of this. What's R? Radius between the ions. So you have X plus and Y minus, the distance between their nuclei, that's the R. So how can you decrease R? What does that mean? That means the ions are closer together in their crystal structure. Okay, now what's Q? Charge. So how can, what's that? Who has a greater charge? NaCl or MgO between them? How do you know? Right, so if we have a +1 and a -1, or a +2 and a -2, that's a game changer. So the bigger the charge, so if you increase charges, +1, +2, +3, -1, -2, -3, and decrease the radius. So the closer these ions are together, think about really strong magnets or weak magnets. The closer they are, the more you feel the pull. Agreed? That's what the R is all about. The charge is the magnitude of the charge here. The higher that is, the stronger the force. So if both of them are at work, it's going to be a really strong compound like MgO. So MgO not only has a +2 and a -1, but Mg +2 has a small radius. Oh, what am I doing? That was weird. O -2 has a small radius. So think about two marbles coming together. The middle of the marbles are going to be really close versus 2 beach balls, right? The middles are going to be pretty far apart. So NaCl, because it has weaker charge, and the radius of both of these is larger than these, they're going to be farther apart. So it's kind of a double whammy, which is why the lattice energy of this is what? This is 3,890 kilojoules per mole, and salt is 788. So what I'm trying to explain, and this is it, this is the whole show for lattice energy, these two concepts. If the magnitude of charge, which is Q, is higher, it's going to have a stronger force. If the radius between the two nuclei is smaller, it's going to have a higher, stronger Coulombic force. Since this one has both of them, small radii and bigger charge, it's a huge difference in lattice energy. Okay? If you compare something like NaCl with LiF, it's not going to be such a big difference. LiF is 1,017 kilojoules per mole. So yeah, it's bigger, but it's not way bigger like this one because it's still +1, -1. It's just lithium's really small, and Li plus is small, and F minus is small. So I'll repeat that again tomorrow, but that's what lattice energy is. That's what it measures, I should say.